Hi, I'm Andrew Arrasmith, and this is the talk I was going to give at the APS March meeting. So this is shot-frugal optimization for variational quantum classical hybrid algorithms. So this was done with Jonas Kubler, Łukasz Cincho, and Patrick Coles, and this is on the archive. So we're talking about variational algorithms, talking about algorithms that use a classical optimization loop where the cost function is evaluated on a quantum device. So there are many examples of that, but some of the more famous ones, trying to find ground states with the variational quantum eigensolver. You can factor integers, you can solve linear systems, you can do principal component analysis in this framework and many more. So all of these types of algorithms require optimization in an environment with some intrinsic uncertainty due to the fact that you're making measurements of a quantum state. And since those measurements take time, you're always going to be dealing with finite statistics and thinking about the precision with which you're measuring, as well as contending with hardware noise. So a very common criticism is then that for a realistically useful application that couldn't be simulated, couldn't be done on a classical computer, you might not be able to do the optimization because you would require so many shots, so many measurements of the quantum state that it would just take too long. So in order to progress with development of these algorithms, we have to stop and think about how to do that optimization. So specifically, we are proposing a optimizer which attempts to be shot frugal and optimize the number of shots it needs for each step in the optimization. And we call this ICANS, which means individual coupled adaptive number of shots. So individual for each gradient component. This is a gradient descent method. And we adapt the number of shots for each gradient component at each step. So to do that, we think about the uncertainty in the gradient and try and forecast what precision we're going to need for our next step so that we don't waste shots getting unnecessary precision. To do that, we take a second order approximation of the cost function. So we do a Taylor expansion and truncate second order, and then use that in conjunction with a Lipschitz constant bound to provide an expected lower bound on how much your cost function improves after that optimization step. So in terms of a cartoon landscape, let's picture that we are doing optimization and our optimizer is currently at the point of the blue circle. We take a gradient. Our estimated gradient says we should take an update step that looks like this. However, there's a lot of uncertainty there, so perhaps we should have taken this update step or that update step instead. With this second order approximation and a Lipschitz bound, we can define what a worst case scenario where the cost function turns up as fast as possible, and thus we use that to decide how precise we need to be. So if this is very tight, then we need to be more precise so we don't end up potentially overshooting and risking going uphill rather than down with the update step. So, making this a little more precise, we advocate using the parameter shift rule to get your gradients. And this is just, you can use two measurements from different quantum states to calculate the gradient of your cost function with respect to your parameters. You get the mean and variance of each partial derivative in the gradient. Then there's an optional step where we consider shrinking the step size if it looks like we're going to have the risk of overshooting. And then we just use the standard gradient descent update rule, but also forecast the precision that we will need for the next step based on what we're seeing. So in equations, this gamma I is the expected lower bound on the improvement due to a particular component of the gradient. Si is the number of shots you allocate for that component. Alpha is your learning rate. L is your Lipschitz constant. Gi is your gradient component. And of course, we have to also, as I said, keep track of the variance. Optimizing that leads you to forecast that you should use this number of shots for the next iteration. And then once you've actually measured the gradient and calculated the variance, if you find they're significantly different from your forecast, it sometimes might be helpful to, for that update step alone, replace alpha by this alpha prime, which would take you to the very bottom of that worst case parabola that I drew. So we're going to then show you how this works. So we're going to consider fixed state input compilation, Heisenberg VQE, and an Ising VQE where we grow the number of qubits and thus the length of the chain. And we're going to use our ICANS method. We're also going to show you how it compares to a sequential optimization by function fitting method, which is also recently proposed specifically for optimization with variational algorithms, as well as ATOM, which is a popular machine learning technique, and SPSA, which has also been around for a while and attempts to use few measurements of an objective function as well. So for the variational compilation task, this is essentially our cost function. We are trying to learn parameters theta to match theta star so that we can replicate this unitary by training parameters here. Theta star is just randomly chosen. So for the results, starting off just with ICANS for the noiseless case. So here we have, of course, finite statistics in all of these measurements, but we ran this on a simulator without any hardware noise simulated. And we find that ICANS 1 particular, so that's the one without the optional adaptation of the learning rate, performed the best in this case. Similarly, for the noisy case, it performs well, though we note that for that particular case, ATOM catches up. And so, just to explain, ATOM 100 means ATOM, where at each gradient evaluation you allow each, for each operator measured, you allow 100 shots. And solve with 1,000 is when you go to fit the function, you allow 1,000 shots. So ICANS looks good compared to a lot of methods. Doesn't have, say, the instability that ATOM sometimes seems to show. And so moving on to the VQE task for the Heisenberg chain, we're instead trying to optimize this quantity, make it as low as possible, where E0 is the ground state energy. Equivalently, for most cases, this is what I'm going to be plotting, but for most cases where you don't know this, you're just trying to minimize trace rho h, where rho is the density matrix and h is your Hamiltonian. And so, again, we find that ICANS does pretty well. So looking at the noiseless case, we find ICANS 2 actually wins this time, so that's with the optional adaptation of the learning rate, and ICANS 1 wins when we do include hardware noise in our simulations. So if we look at how this scales with increasing number of qubits though, because each of those were for small systems, we find that actually ICANS continues to scale. No magic happens. When you increase the number of qubits, you increase the number of parameters you have to train, so it does take longer. So you'll notice that none of the optimizers get quite as far as you go up to more sites. However, ICANS continues to perform well and stays out ahead of the other optimizers for this task. So, in conclusion, variational hyperalgorithms are a promising approach towards getting quantum computers to be useful sooner. But we're going to have to be careful with how we do our optimization so that we don't shift computational complexity to into where it's just hidden in the number of measurements we have to take. And so we advocate using optimizers that can adapt the number of shots used, so you can try and be frugal with that resource. So thank you. Here is the archive posting again. Thanks for watching.